Let's work on a few more examples on finding the vector equation of a line. Feel free to pause the video at the start of each question, have a go for yourself, and then see how you go. The first question, it's just going to be a reminder of what we went through in the first video. It says find the vector equation of a line containing the points 3i take 4j plus 2k and minus 2i plus 6j and minus 2k. So first of all, I'm just going to write down let a equal, and I'm just going to write this as a vector, 3, minus 4 and 2, so that's my vector A, and I'm going to let vector B be the other vector, 2, 6, and minus 2. In the first video, what we saw was that find the vector equation of a line, we just need a point in the line A, and we need the direction of the line going from A to B. The next thing I'm going to find is this direction vector AB. So the vector AB, me vector B, so minus 2, 6, minus 2, take away the first vector, which is 3, minus 4, and 2. So minus 2, minus 3 is minus 5. 6, take away minus 4 is 6 plus 4 is 10. Minus 2 gives us 0. Now, we've got a point in the line, we've got the direction of the line, so we can write the equation line. So the vector equation of the line going through A and B is going to be 3, negative 4, 2. So that's point A. And then we're going to add lambda times vector AB, which is negative 5, 10, and 0. And again, the question is given to us in component form, so I'll just write my answer in component form as well. So x matches with x, so 3 take away 5 lambda I direction plus minus 4 plus 10 lambda, and that's going in the J direction, and then we've got plus 2 plus no lambdas in the A direction. The second question we have is a little bit different. Find the vector equation of the line that passes through a point and is parallel to the vector 2, 1, 1. So when we think about it, we've got our point up here, we'll call this point A for now. And we know that it has to be parallel to this vector here, 2, 1, 1. So I'm just going to assume that, let's call this just a B for now, and that's vector B over there. What we know about vectors is that we can move them around in three-dimensional space. So I could take this vector B, and I could just write the same vector B up here. Now, if we do R equals A plus lambda B, what we have is the line going through A in the direction of B. And obviously this line is parallel to this line over here, because they're both traveling in the same direction. Parallel lines travel in the same direction, they never cross, they're the same distance apart at every point on the line. So this is quite an easy question because they've given us all the information. So we've got A, so we're going to write this as 4, 3, and 1 plus lambda, and we know the direction is going to be the same as direction B, so it's going to be 2, 1, and 1. Now the third question is just a little bit different to the other two. Now we're just trying to determine if a point is on the line. So we know that we can write R as an x, y coordinate. So we've got R equals xy equals 2 plus lambda, and we have 4 plus 3 lambda. We want to know if this point lies on this line here. So I want to know, does minus 2 minus 8, is there some value of lambda that makes this true? So what we've got is minus 2 equals 2 plus lambda, and we've also got minus 8 equals 4 plus 3 lambda. I'm going to work on the left hand side for now. Let's solve for the lambda for the x coordinate. So if we're solving for lambda for the x coordinate, we should end up with lambda is negative 4. And if we try to solve for lambda on this side, we're going to have minus 12 equals 3 lambda. So lambda equals minus 4. Now, because the lambda for the x coordinate and the lambda for the y coordinate are the same, therefore, minus 2 minus 8 equals 2, 4 minus 4 lots of 1 and 3. Therefore, the point -2, -8 does lie on the line. Okay, and the reason why it lies on the line is because there was a lambda value that gave us the coordinate -2, -8. Now the fourth example is fairly similar to the third example. We're asking, does the point 405 lie on the line with this vector equation here? And the only difference is that we're dealing with 3 coordinates, which is different to the previous example, which I was only dealing with 2 coordinates. So again, we'll set it up the same way. We know that because we're dealing with 3 coordinates, it's our x, y, z's. And our x, y, z's are going to come out determined by the lambda value. So we've got 4, take away 2 lambda, and 1 plus lambda. Now we want to know, is there a lambda value that's the same for all 3 of these? That will give us these values of 4, 0, and 5. Minus 2 plus 3 lambda, 4 take away 2 lambda, and 1 plus. And again, we can break this up into the 3 components. So the x component is 4 equals minus 2 plus 3 lambda. The y component is 0 equals 4 take away 2 lambda. And the z component is 5 equals 1 plus lambda. Now when we're solving the x coordinates, we'll bring the 2 across. We'll have 6 equals 3 lambda, and we'll have lambda equals 2. When we check the y coordinate, what we can do is we've got 2 lambda is 4, lambda is 2. Okay, so far for the x and the y coordinate, it's working quite nicely. When we look at the z coordinate though, we end up with the lambda equals 4. Okay. Now, because we're getting a lambda of 2 for our xy and a lambda of 4 for our z values, make this statement true. There does not exist a lambda value such that (4, 0, 5) equals minus 2, 4, 1 plus lambda 3, -2. Okay, so this point does not lie on this line. Therefore, your 4, 0, 5 does not lie. Let's just see how we could answer this question in ClassPad to quickly determine if that point does lie on the line. What I'm going to do is I'm just going to set up a simultaneous equation here. And what I'll do is I'm going to use a different variable for each of these lambdas. So use one for the x, one for the y, one for the z. And just to make life easier, I'll use the x, y, and z. So the first equation we're going to use is for the x, so 4 equals minus 2 plus 3x. Second equation is for the y, 0 equals 4 minus 2y. Now I'm not saying that that's the y or the x value, I'm just plugging those in. And the last one we've got is 5 equals 1 plus z. Now again, I'm just representing the lambdas by these variables here because they're quite convenient on the ClassPad keyboard. You can see there. And we're solving for x, y, and z. When we solve this equation, what you should find is that if it is a point, the x, y, and the z's will all be the same. In this case, we can see x is 2, y is 2, and z is 4, which is what we had before. So because these values of lambda are not all the same, this point does not lie on this line. If we go back to the previous example, and if we solve these two equations here, so minus 2, I like to just clear all the variables before I do anything. Minus 2 equals 2 plus x, and here we've got minus 8 equals 4 plus 3x, 3y. And we'll solve it for x and y. And here you can see that the values are the same for x and y, which means that the lambda values are the same here. Because the values of lambda are the same, it means that this point does lie on the line. The point -2, 8 does lie on this line, because there does exist a lambda value that allows us to